Shorformer better language modeling using shorter input. It's a very interesting concept. Why is this paper special? It proposes a stage chaining method, which allows you to you train the model with shorter sequences first. Then in the later stage, you feed longer sequences in the model training. They found out if you use this training routine, your model will have a better training efficiency and also a better performance. And they also propose a ways to let the model be able to cache and to condition on the previously processed sequence. Let's say we have 2 sequences, and the model is processing sequence number 2. In the traditional way, the transformer has no way to access the information in the sequence number 1. So that's really becoming a problem. And this paper proposed a way, they basically modify the positional embeddings and the edits on cache mechanisms to let the model be able to access the information that happened in the previous sequence. And how they do that, they added positional embedding in queries and the keys instead of values. That's very innovative and groundbreaking idea. In terms of the results, they are able to speed up the training speed by 65%, and in the generation speed, they can speed up to 9x, which is tremendous results. Even when doing this, they can have already more efficient training and inference. They also can lower the perplexity on the Wikipedia text 103 compared to the baseline transformer. By the way, I make deep learning explainer videos every week. If you would like to receive more relevant videos like this, don't forget to subscribe. Your subscription is also the best encouragement for me to make more videos like this. Paper is a joint work between Washington University, Facebook AI, and the Allen Institute. Okay, so let's just look at some problems with modeling long sequences. Long sequences means they are very long. You have many tokens, and the current transformer architecture is not limited by the math. It's limited by your GPU memory, because you only can fix certain number of tokens at the same time. That means if you are going to process a sequence that's super long, you will need to segment the sequence into smaller subsequences and process those subsequences at a time, like one by one. And the problem is, when you process those subsequences, you won't be able to access the information from previous sequences. That will hurt your language modeling a lot, because sometimes you really need a very long dependencies to model certain things. And this is what this paper tries to address. To understand early token curves a little bit better, we need to understand there are actually 2 different ways of evaluating a language model: non-overlapping and sliding window. Early token curves only happen when you use non-overlapping evaluation method. So let's just look into it. Let's say your transformer only have very little GPU memory, and the max amount of tokens you can fit is 2. So that in this case, you will need to divide this sequence. This is your target sequence. You want to predict this. You want to use this to evaluate your model. You need to divide this to 2 plus 1 and 2 plus 1, and you will get the prompt depending on how you define your methods. And usually you can get a prompt for first token, then you will need to predict the next token would. And when you predict the first token and second tokens, you need to predict the next token like. So the model will do this one by one in your subsequence. But the problem happens when you do the second sequence evaluation. Why? Because first of all, you won't have any prompts, so your model need to guess these first tokens. Okay, that's fine. That you just guess. Basically, you couldn't get it right at all. Then you got the answer. When you got the answer, you try to predict the next tokens. So now you have one context. Okay, so you have 2. Then you need to use this one context to predict the next token due. So you realize now you actually already experience early token curves, because the early tokens in this sequence number 2, you don't have any context when you're trying to predict the token to. When you're trying to predict a token do, you only have one previous context instead of the real previous context is actually 4. Now you only have one previous context tokens. So it's very hard to predict to do, and probably much easier to when you need to predict the tokens, the last token it, because you already have the previous 2 tokens. So this is the what we call early token curse. They happen when you segment your subsequences, your sequence into subsequences and use non-overlapping evaluation method. So let's just look into the sliding window methods. Basically, you also have the same constraint. Your max token is 2. You only can fit your transformer 2 context tokens at a time. So you still divided this, and in the first section here, that's actually no problem. Let's just say you have prompt and predict would, you have I would and predict like. Then the true difference happen here when you have the because it's sliding window. So after you predict the first 3 tokens, you slide your window a little bit. So your stride is 1 now. So you only move 1 tokens to your windows at a time. Then your window is basically 2. Then you have context would like. So when you predict the token, your target token to, you at least have 2 contexts would like. And it's much easier to predict this token correctly when you have this context. And on the contrary, in the previous, the non-overlapping, when you're trying to predict 2, you basically have 0 context. So that means you need to guess. So that's the difference. So when you do a sliding window, there's no early token curse. But why people are still using non-overlapping? Because it's much faster. Because if you notice, you need to move your windows 1 token at a time. So it means every time you need to your transformer need to process, need to reproduce this context, the presentation of previous tokens. That means you need to run a lot of time. For example, in this case, you will need to first of all run 1, 2, 3, 4. Basically, you will roughly need to predict number of your context words, your window context plus a number of your window context. This is approximately the maximum stride, maximum operations that you need to do is this. So you need to do a lot of overlapping calculation because you only move 1 tokens at a time, and every time you need to recalculate the previous token's context. That means your inference will be extremely slow, much more slow than the previous one. So it's more like maybe L squared versus L. This is just approximately. Okay, so to adjust these things, we need to find a way to combine the strengths of sliding window, which is being able to access the previous context, and the speed of non-overlapping evaluation methods, which is what this paper trying to do. So the effective context window size. So let's say your window size is L. Let's say your window size is L. In the non-overlapping solutions, that means you segment your sequence to the subsequence, the length of L. And in the sliding window solution, that means your sliding window size is L. And another definition, another term you need to know is a stride. Stride means in the sliding windows, how much steps you need to take, you need to slide at a time. In this situation, that's defined as ACE. So we can calculate effective context window size, because in a non-overlapping, that means your sequence, your subsequence, when you're doing the inference in your subsequence, you will have the context from 0, which means the first token, you have 0 context, to the last token, which means you have L context. So your effective context size is from 0 to L. In the sliding window, your context size, no matter what, you will have L plus S, because let's say your L is 10, means your transformer can fit 10 tokens at a time. Then your stride is 2. That means you stride 2 tokens at a time. When you first predict the first 10 tokens, then you have these 10 tokens as context, but you will stride to another token. So this means 10 plus 2, then you have only 8 previous tokens as your context. So no matter what, your effective context window size for the sliding window will be much larger than the non-overlapping solutions. That's why sliding windows has always better performance. How much context size affects transformers? It's actually a lot, because up to the L time steps where the model can attend to all the input tokens when predicting L plus 1. If you have L context size, your model can attend to at least L tokens. That means it can access L previous tokens context. So that will be very, very different. So let's just look at the experiment results. So this is a non-overlapping. We can see if you increase your subsequence length with your L, then your perplexity will become much lower, because every time you have much more context. So let's look into the experiment results. We can take a look at the non-overlapping first. You can see when you increase your subsequence length, which means you will have more context as it become longer, then the perplexity of it increases accordingly. And the speed, actually, this speed, how we can interpret this speed is a number of tokens that they can be processed at a time. And it's generally increased because you increase the parallelism in your GPUs. Means like you can process more different tokens at the same time. In general, its perplexity is reduced a lot when you increase it to 3000. Let's look into the sliding windows, token by token. The stride equals to 1. And when you increase your subsequence length, its perplexity is increased from 24, reduced from 24 to 17. And if you look at the speed, when you increase your subsequence length, which means your window size become larger, then your speed become much slower. Why? If you remember the previous example I showed you, when you increase your window size, that means you need to do more overlapping calculation when you use a sliding window. Because you only move one stride at a time. Every time you need to calculate the previous L minus 1 tokens. In this case, you only need to calculate 31 tokens when you predict 1 token. In this case, you need to calculate 3071 tokens when you predict 1 token. And you need to do this many times for many tokens. So that's why your speed becomes extremely slow. And compared to the non-overlapping, it's just non-comparable. One is 5 tokens at a time, another is 15,000 tokens at a time. So how much difference? It's 3,000 times difference. Okay, 3,000 times faster. And in terms of performance, sliding window is definitely more accurate. The conclusion we have so far: increasing the minimum effective window size is more important than increasing the maximum one. By the way, this is the experiments they run in 16-layer transformer on Wikipedia 103. This is the result that you see with different window size and in the overlapping and the sliding window methods. Okay, so next we want to cover some stage chaining. It's a way that you train your transformer language models with shorter utterances at first, then you feed the longer utterances in the second stage. And the experiment is the same. They use the B&A transformers, which is 16-layer transformers. And if you want to read more details about these transformers, look into the paper. It has all hyperparameters. And the good thing is because of these transformers, most transformers are using the non-learnable positional embeddings. If you use non-learnable positional embeddings, it basically doesn't matter your training is long or short sequences and the order of your long and short sequences, because the positional embeddings is just generated by sinusoidal waves. You can see there's a kind of unique ID for each different position. It's just generated, it's not learnable. And if you use some learn embeddings, learn positional embedding, you have a problem because your model will learn some BIOS. If you feed the short occurrences in the stage 1, you will only learn those short position, like position maybe 1 to position 200, and later on you feed the 2000 3000 tokens at the same time, then your model won't be able to handle those high positions doing the training that much. So that's the benefit of using standard transformer models. And this is the result of stage chaining. So let's just try to interpret these results. The x-axis is initial stage subsequence length, means stage 1. There are 2 stages. Stage 1, which means we only feed the short occurrences. Initial stage subsequence length, you can see it ranges from 32 to 1536. And when you increase the initial subsequences length, there's a certain trend. If you increase that to too much, too long, you need to spend more time. You can see you need to spend more time to reach the performance that's comparable to the baseline. This is the number of, the y-axis is basically the number of epochs that you do in your stage 1 training. And if you increase this number of epochs to like a lot, too much is also not good. And the initial stage training subsequence length, too much is also not good. So the best combination is roughly like 128 for your short subsequence length, and only train on 100 epochs. In the whole training, the number of epochs will always be 205 in this experiment. So if you train 200 epochs in your short sequences stage 1, that means you will only have 5 epochs in the long sequence lenses. Long sequence training. Okay, and you will see some of the places are blank, and the reason of that is they never reach the comparable results to the baseline performance. And this is a ratio. So if you see this number is 0.5, 0.4, means you only need 40% of time to reach the baseline's performance. And this is the perplexity, and the baseline model's perplexity is 18.65. So those numbers in colors means they are outperforming the baseline model. And you can see the best combination is always 128. If you choose your stage 1 subsequence length as 128, you can most likely outperform the baseline model by quite a lot. This also reflects to the time that you need to match the baseline model performance, because in the previous picture you can see number of epochs you need to do in the stage 1 is around 50 to 100, and in this also reflects that kind of trend. And if you have too long sequence length for your stage 1, your performance basically won't be too good. You can see in the 1500 columns. Okay, so this is quite interesting how you can stage your training. And this actually challenges the assumption that the longer sequences you feed into your model for training, the better. Basically, it's not necessary. It's very counterintuitive, I know. They just prove that if you feed the short sequences first, then after that feed the longer sequences, you will have the better results. Yeah, it's very intriguing. I was wondering if there's any meanings, like linguistic meaning of doing this. I don't know yet, but it's definitely worth exploring more in the future. This stage chaining can make so much difference. You can see the difference is actually very big. The best performing model is 17.5, is 1.1 perplexity lower than the baseline model, and you don't have to change anything. You only need to change the training routine, then there'll be so much different. Amazing. It's definitely worth exploring more. So we know how the context window size affect the transformer performance. So what if we can cache the previous context, also not increase the actual context window size? Why will happen? How can we do that? So the solution is to repositioning position embeddings. So now, like we know, sliding window is very good because we can always have a lot of context, but evaluations inference time is very slow. The solution the other people came up so far is to cache that, and that's why people propose Transformer XL, which is a way that you use relative position embeddings to lay the transformer to be able to cache the previous context. But relative position embeddings is very slow, and you need to have more parameters, more memories. That's why this paper proposes something new. And before we dive in that, we need to understand how the positional embeddings works in Transformer. So basically, it's quite simple. You firstly embed each word into one vector. So you will have the tensor X that represents the vectors of every token. Then you generate precision embeddings tensors, which is P. So every vector will have every dimension will have their own positional embeddings. And you do the addition to your tensor X and the tensor P. Then you have a new tensor which will contain the positional information. You do the self-attention, which your key query value or the new generated X. This X plus P will become a new X. And that means your key query value, all these three things have positional information. The problem is if you doing cache with those things, your cache will contain the position information that was in the previous sequence, and in the new sequence you are doing inference now, the token's position will change. So how can you address that, right? That's why they propose this position-infused attention. So the goal is to the output, the value here contains no any position information. They found out if it's actually quite straightforward, but I also never thought about this. But once they pointed this out, it's very easy to understand. You just need to put your position embeddings, positional information in your query and the key, and you don't put it in the value. So your self-attention will become, your key will become tensor X plus position embeddings, tensor X plus position embedding for query and for key, but your value is just a pure representation of tokens, contains no position information. And why this will change everything is they actually change everything. Yeah. So your queue and the key contain positional information, but they do you end up doing inner products between query and the key, so they will become a scalar. Because scalars basically don't contain anything. They're just the way they let you aggregate your value. Then end up you will become maybe first some scalar from 0 to 1 to your each tokens. They tells you when you processing these tokens which other tokens are most important. That's what the attention mechanism tells you. As long as you don't add the position information in your value, you will end up not having stored anything about information in your value. And that's good. In the procedure that needs the position information must, which is here, the only add it here and remove the information of position here. So that's a very smart move. Extremely smart. So because of PIA, position-infused attention, it enables caching. Now we can reuse the LO -1 of previous output at every layer without actually needing to compute them again. And the attention complexity is reduced from L squared to L. Why? Because now we only have one query, which is the new tokens. Because you slide one stride at a time. So you will always have move to one token forward. You will have one new token, which will be your new query. You will have keys, which is L minus 1 of previous tokens plus your new tokens. So you will have L keys. Now you only need to do L times of this inner product instead of L square. It's very useful. This mechanism is very useful in modeling super long text because you don't have to calculate everything. When you segment your sequence to subsequences, you don't have to calculate, or you use sliding windows. You don't have to calculate everything from scratch again. So it's a super innovative way. Personally, I think I already been thinking this how we can apply these mechanisms, new mechanism, caching mechanism. I personally think this mechanism, this new attention mechanism, is a game changer. Why? Because it allows you to access the previous hidden state in a very easy way. You just feels like you have another recurrent neural network on top of a transformer, so that you can always access the previous information. Since they say you have 1 million long sequence, now we can divide it into a lot of subsequences, and we still will be able to connect this previous information across different subsequences. The only thing is the gradient couldn't flow across those subsequences. That's the only difference between this using this PIA and the recurrent neural networks. Okay, so let's just look at the result. It's Wikipedia. This is they're using the PIA Position-infused attention models to run on L new tokens and L cache tokens. Here you can see compared to the baseline. Baseline is a transformer model without using PIA, and this is the non-overlapping evaluation, so it's has higher perplexity, and the sliding window has a lower perplexity. For these PIA models, they all use non-overlapping evaluation methods, and they always have L, the segment is L, and the previous L cache. Okay, so the subsequence length ranges from 32 to 1500, and you can see the subsequence length was set up for 512. It gets a best result, and the best performing PIA models, it actually outperform the sliding window transformer. So it's amazing. It's non-overlapping stuff, but using the cache is now able to outperform the transformer model using sliding windows. And not to mention, it's much faster. Its speed is comparable to the non-overlapping transformer model, but has this the same performance. It has even better performance compared to the sliding window model. And the speed you can see the sliding window of the transformer is it only can process 5 tokens 1 second. And the new model, PIA model, it can process over 20,000 tokens, and it still has a better result than this. So if you just do the math, it's 4,000 times faster, and even have better result. So it's super amazing. If we previously did some stage training, and what if we combine PIA and the stage training? What will happen? So this is what I call Shortformer. Shortformer is stage training plus positional-infused attention transformer. So compare to these things, this is PIA without stage training. If you plug in the stage training, your perplexity will be even lower. And this is the Shortformers compared to the other baseline models. You can see the baseline models here, and the Shortformer speed is almost as fast as a baseline model. Because why is it slightly slower? Because you need to do some cache, and this is a non-overlapping baseline model. So you need to do some cache. Even you are still, the Shortformer is non-overlapping, but it still need to cache the previous subsequence. So it will be slightly, at least need to read the cache and then need to do the more queries than non-overlapping transformer. So it was slightly slower than that. It's 1% slower than that. But the perplexity is much better. It's 1.2 lower than the baseline model, the non-overlapping, and also lower than the sliding window one. So it's a very, very superior method. Definitely, if you compare to the state-of-the-art, which is KNN language model, it's still not comparable. But compared to the other transformer-based model, it's really, really good. It's really, really good. As for this, Shortformer compared to the baseline plus stage chaining. The baseline plus stage chaining, which is transformer, PIA Shortformer plus stage chaining, it has a better perplexity, but the speed is 9 times slower. So I would say Shortformer is quite a good trade-off. It has the good speed and the good accuracy. So if you only remember one thing from this video, there will be position-infused attention. It has so much potential. I believe in the future work, there will be more papers using this to model super long stuff, maybe turn-taking conversations or novel or super long documents. They will be super interesting. So a summary of this paper, it proposes stage training. It argued that if you use stage training, you don't need to change anything, then your transformer language model will have much better performance. And it proposed the PIA position-infused embeddings. You only add the position embeddings to queries and the keys. Then you will not store any information about position in your cache, so that you can easily to use your cache from the previous process, so that you can easily use your cache from the previous process subsequence. And by doing this, your training speed will be speed up a lot. This is the contribution from stage training, and the generation time, inference time will speed up 9x, which is the contribution from the position-infused embedding. Which is a contribution from position-infused attention. And lastly, it successfully lowered the perplexity on Wikipedia text 103 by quite a significant margin compared to the baseline. If you enjoyed the video, give it a like or leave a comment. I will reply all of them. And don't forget to subscribe for more relevant deep learning videos like this. Other than that, take care. Until next time.